Hi everybody, my name is Jean-François Hermant. I am an associate professor of computer science at ICI Paris, a French graduate school of engineering located in Paris, France. Today in this talk, we'll see how to use Maple to solve real-time scheduling problems. This talk is devoted to the study of real-time scheduling problems that arise when considering a processor. I'll start with the presentation of the problem. What are the assumptions? What are the properties that we want to achieve? I'll present the solutions to this problem. We'll see that there are two main classes of solution, those based on fixed priority scheduling algorithms and those based on deadline-driven scheduling algorithm. Then I'll present the associated feasibility conditions. We'll see that this feasibility condition can be based on predicates and or on worst-case response times. In the first part of this talk, I present the Maple implementation of the feasibility condition for fixed priority scheduling algorithms, such as highest priority first deadline monotonic, or rate monotonic, and deadline-driven scheduling algorithm, such as earliest deadline first, when all the task parameters, that is the worst-case execution times, the inter-arrival times or periods, and the deadlines are known and fixed. We'll see that the Maple implementation is straightforward and provides an efficient dimensioning tool. Then I present the feasibility domain for EDF, which is a generalization of the classical results in real-time scheduling theory. I present the C-space, its convexity, and its parametric equations. We'll see how to define an optimization problem and how to apply the simplex algorithm to eliminate all the redundant constraints and to provide an efficient and elegant computation of the feasibility domain for EDF. In the second part of this talk, I present the Maple implementation of the feasibility domain for EDF when the worst-case execution times of the task, the Cs, are unknown and variable, and when the other task parameters, the Ts and the Ds, are known and fixed. The definition of the program. Here we want to schedule a task set tau on a processor. This task set is composed of n tasks, tau1, tau n. Each task tau I is characterized by Ci, its worst case execution time, Ti, its minimum inter-arrival time or period, and Di, its relative deadline. We want to know whether the task set is feasible, that is, if all the deadlines are always met or not for a given scheduling algorithm. We consider fixed priority scheduling algorithms such as HPF-DM, HPF-RM, and HPF-Hotsley. HPF is the acronym for highest priority first. It's an online scheduling algorithm. DM is the acronym for deadline monotonic. It's a priority assignment method. The highest priority is assigned to the task with the shortest deadline. RM is the acronym for rate monotonic. It's a priority assignment method. The highest priority is assigned to the task with the shortest period. Hotsley is an optimal priority assignment method. It's a branch and bound algorithm which finds a solution if one exists. Any task set feasible with HPF-RM or HPF-DM is feasible with HPF-Hotsley. We consider deadline-driven scheduling algorithms such as EDF. EDF is the acronym for earliest deadline first. It's an online scheduling algorithm. It's an optimal scheduling algorithm. Any task set feasible with a fixed priority scheduling algorithm is feasible with EDF. Let us now consider the following example. Task set tau is composed of three tasks, tau1, tau2, tau3. The task parameters are given. For tau1, we have C1 equal to 2, tau1 equal to 7, D1 equal to 5. For tau2, we have C2 equal to 3, T2 equal to 11, and D2 equal to 7. For the 3, we have C3 equal to 5, D3 equal to 13, and D3 equal to 10. Here is the EDF schedule for task set 2. Each time there is an activation request for a task to I at a time t, we compute its absolute deadline t plus di. All the tasks are sorted in an increasing order according to their absolute deadlines. The task with the earliest absolute deadline is always scheduled first. The activation requests are the green arrows. The absolute deadlines are the red arrows. In this example, we see that no deadlines are missed over time interval 0, 40. We'll see later that it is sufficient to prove that task set 2 is always feasible with EDF. Here is the HPF DM schedule for the same task set 2. The highest priority is assigned to the task with the shortest relative deadline. In this example, the highest priority is assigned to task TO1. The intermediate priority is assigned to task TO2, and the lowest priority is assigned to task TO3. The activation requests are the green arrows. The absolute deadlines are the red arrows. We see that task TO3 always misses its deadline. Hence, task set 2 is clearly not feasible with HPF DM. When we want to solve a real-time scheduling problem, we must provide feasibility condition. This is mandatory. There are 3 kinds of feasibility condition: necessary feasibility condition, necessary and sufficient feasibility condition, and sufficient feasibility condition. With necessary feasibility condition, we have 2 is feasible. It implies that the necessary feasibility conditions are satisfied. With necessary and sufficient feasibility condition, we have 2 is feasible if and only if necessary and sufficient feasibility conditions are satisfied. And with sufficient feasibility condition, we have sufficient feasibility conditions are satisfied. It implies that 2 is feasible. In the sequence, we focus on the necessary and sufficient feasibility condition. We consider the general case where deadlines and periods are independent. Feasibility condition can be based on predicates. This is true for EDF. Here is the necessary and sufficient feasibility condition for EDF based on the processor demand function h of t. This function captures the dynamic behavior of EDF. Feasibility conditions can be based on worst case response time. This is true for both fixed priority scheduling algorithms and deadline-driven scheduling algorithms. The necessary and sufficient feasibility condition based on worst case response time are written as follows. For each task to I, we compute its worst case response time Ri, and we check if it is less than its relative deadline Di. This is useful to analyze a distributed system with a holistic approach or a trajectory approach, for instance. Worst case response times for fixed priority scheduling algorithms are based on the computation of busy periods, which are periods of time during which the processor is busy scheduling tasks with a given priority. Here we have an activation request for a task to I at a time A. We compute the busy period during which the processor is busy scheduling all the tasks with a priority greater than or equal to that of task to I. Task to I completes its execution at the end of the busy period. Hence, we are able to compute its worst case response time and to check if it completes its execution before its deadline. The necessary and sufficient feasibility conditions for fixed priority scheduling algorithms are written as follows. The busy periods are computed as follows. We have step functions, and we need to compute fixed points. This is done by successive iterations. We can compute worst-case response time for EDF as well. The necessary and sufficient feasibility conditions for deadline-driven scheduling algorithms are written as follows. The computation of the busy periods is a bit more complex for deadline-driven scheduling algorithms than for fixed priority scheduling algorithms, but the reasoning is the same. FCs are based on predicates or on worst-case response times for EDF. They are based on worst-case response time for HPF DM, HPF RM, and HPF Huxley. Computation are done over bounded time intervals, and complexity is pseudo-polynomial. The Maple implementation of the feasibility condition for fixed priority scheduling algorithms, HPFDM or HPFRM, and deadline-driven scheduling algorithm, EDF, when all the task parameters, C, T, T, are known and fixed, is given in the Maple worksheets number 1 and number 2. The implementation is straightforward and provides an efficient dimensioning tool. Now I'll present the feasibility domain for EDF, which is a generalization of the classical result in real-time scheduling theory. I present the C-space, its convexity, and its parametric equations. We'll see how to define an optimization program and how to apply the simplex algorithm to eliminate all the redundant constraints and to provide an efficient and elegant computation of the feasibility domain for EDF. The feasibility domain for EDF, or C-space, is defined as the set of all the task sets that are feasible with EDF. That is, all the task sets with the sup or the max of h of t divided by t less than or equal to 1. This is another way to write the necessary and sufficient feasibility condition for EDF. In the sequel, the worst-case execution times of the task, the C's, are unknown and variable, while the other task parameters, the T's and the D's, are known and fixed. We can prove the following theorem, which is central to our demonstration, and which allows to characterize the feasibility domain, or C-space, for EDF. We can easily show that the feasibility domain, or C-space, for EDF is convex. We have these three relationships. We have a finite set of constraints, see the previous theorem. We want to reduce this set, that is to find the minimum set of constraints that characterizes the convex feasibility domain for EDF. To remove all the redundant constraints, we solve an optimization problem with the simplex algorithm. The optimization problem can be written as follows. We maximize the objective function h of ti under all the constraints, except the one that is under consideration, and we compare the value that is computed to ti to decide if we keep these constraints or not. Ti is a discontinuity point of the processor demand function h of t. In other terms, ti is an absolute deadline. N is the number of tasks, for example, 3, if we consider 3 tasks in order to represent the C-space in 3 dimensions. M is the number of constraints, which is given by the number of discontinuity points of the processor demand function h of t over time interval 0, the least common multiple of the task periods. We apply the simplex algorithm to remove all the redundant constraints. We derive the parametric equation of the feasibility domain for EDF. the Maple implementation of the feasibility domain for EDF, when the worst case execution times of the task, the C's, are unknown and variable, and when the other task parameters, the T's and the D's, are known and fixed, is given in the Maple worksheet number 3. We provide an efficient and elegant computation of the feasibility domain for EDF. I'll switch to the Maple worksheet. So here we have our task set, TO, composed of 3 tasks, TO1, TO2, TO3. The worst case execution times are unknown and variable. So we have variable X for C1, variable Y for C2, and variable Z for C3. And the periods and deadlines are set. We have T1 equal to 7, D1 equal to 5, T2 equal to 11, D2 equal to 7, T3 equal to 13, and D3 equal to 10. So here we have our task parameters. We compute the processor demand. So here we have the processor demand function h of t. So this is the definition. For this example, we have this function h of t. We compute the absolute deadlines of the task set for task TO1, for task TO2, for task TO3. So we have all the discontinuity points of the processor demand function h of t. So this is the set S. So we compute the cardinal of this set, so the number of constraints. We see that in this example, we have 281 constraints. So we start with all these constraints. We apply, we solve the optimization problem. We maximize the objective function h of t under all the constraints, except the one that is under consideration. And we compare the value that is computed. So this objective function to t to decide if we keep these constraints or not. T is a discontinuity point of the processor demand function h of t. So t is an absolute deadline. And here we have n equal to 3, we have 3 tasks, and m is equal to 281. We apply the simplex algorithm to remove all the redundant constraints. So you see, for this example, we start with 281 constraints, and at the end, we have only this 5 constraints left. And it takes about 35 seconds to remove all the redundant constraints. So this is an efficient and elegant computation of the feasibility domain for EDF. I'll switch back to the presentation. So we consider the following example. Task set TO is composed of 3 tasks, TO1, TO2, TO3. We know that the worst case execution times are unknown and variables, and the periods and the deadlines are set as follows. After removing all the redundant constraints, we get this tiny expression of the feasibility domain for EDF. Here are the parametric equations characterizing the feasibility domain or C-space for EDF. The feasibility domain or C-space for EDF is convex, which is directly related to the optimality of EDF. It is defined as follows. So, to conclude, The first part of this talk focuses on the Maple implementation of the feasibility condition for fixed priority scheduling algorithm, HPF rate monotonic, HPF deadline monotonic, and deadline-driven scheduling algorithm, EDF, when all the task parameters, the C, the T, the D, are known and fixed. The necessary, and sufficient feasibility condition for these algorithms are implemented on Maple. The implementation is straightforward and provide an efficient dimensioning tool. So these are the Maple worksheet number 1 and number 2. The second part of this talk focuses on the Maple implementation of the necessary and sufficient feasibility condition for EDF, when the worst case execution times of the task, the Cs, are unknown and variable, and when the other task parameters, the T's and the D's, are known and fixed. We show that the feasibility domain for EDF is convex, which is directly related to the optimality of EDF. The simplex algorithm is used to eliminate all the redundant constraints and to provide an efficient and elegant computation of the feasibility domain. So this is the Maple worksheet number 3. These results can be used to compare fixed priority scheduling algorithm, HPF RM or HPF DM, and deadline-driven scheduling algorithms, EDF, in terms of efficiency. Thank you for your attention.